Welcome to the introduction of basic operation and troubleshooting for the Caterpillar EUI fuel system. This presentation is a generalized introduction of the features, system operation, and troubleshooting basics for Caterpillar engines using the mechanically actuated, electronically controlled unit injector fuel system. This presentation is not intended to replace the Caterpillar service manual or other service publications. For detailed troubleshooting information, always refer to the latest service publications. The EUI fuel system has been used on most new 10 to 16-liter displacement models of Caterpillar electronic truck and industrial engines introduced since 1988. This fuel system provides very high injection pressures and full authority electronic control for optimal engine performance, fuel economy, and exhaust emissions. Applications include the 3176, 3196, C10, C12, and 3406E engine families. This presentation covers 4 topics: the electronic engine families using EUI, the operation of the EUI fuel system, the operation of the electronic control system, and finally, basic fuel system troubleshooting. Since its introduction in 1988, the EUI fuel system has undergone many design changes to add features and improve performance and reliability. However, the operation and troubleshooting of all EUI systems is very similar. This presentation uses a generalized example of a system with the latest features. The 10-liter displacement 3176 engine was the first Caterpillar engine to use the EUI fuel system. Introduced in 1988, the 3176 was primarily a heavy-duty on-highway truck engine, but was also used in some industrial and marine applications. In 1996, the C10 and C12 were introduced for the on-highway truck market. The same engines were designated the 3176C, 3196 for the industrial and marine markets. The C10, C12, and 3176C, 3196 engines all incorporate several major improvements, including a higher pressure EUI fuel system and improved electronic control system. Caterpillar introduced the first 3406 engine in 1973. The newest version is the 3406E, which is the 14 and 16-liter heavy-duty on-highway engine. Introduced in 1993, the original 3406E was the first 14-liter truck engine to use EUI over the former pump and line system. In 1998, a 16-liter high-horsepower version was added to the 14-liter models of the 3406E truck engine. All 3406E engines use the high-pressure EUI fuel system and advanced electronic control system, similar to the C10 and C12. The EUI fuel system is comprised of 2 subsystems, mechanical and electronic. The mechanical system consists of the low-pressure fuel supply system and EUI injectors. These components produce very high injection pressures of up to 30,000 psi and provide precise control of fuel delivery. This results in improved fuel economy and reduced exhaust emissions. The electronic control system provides full authority electronic control of all engine functions. New features include electronic speed governing, cold startup mode strategy, automatic altitude compensation, variable injection timing, and oil pressure and coolant warnings and derate. These features result in precise engine speed control, unmatched cold starting, low smoke and emissions under all operating conditions, and built-in engine protection. The EUI fuel system and electronics are virtually adjustment-free. Most changes to engine horsepower or performance characteristics are accomplished by installing new electronic software or upgraded mechanical components. To repair the system, first identify and then replace the faulty component. All system components, including the injectors, electronic sensors, harnesses, connectors, and electronic control module, are dealer serviceable. This allows faster repair times and eliminates the need to rely on the fuel system repair shop to make component repairs and adjustments. The operation of the EUI fuel system is quite different from that of previous fuel systems. In order to troubleshoot an EUI system effectively, you must have a basic understanding of how it works. To help you learn the basics of the EUI system, we'll introduce each system component and then show how these components work together. The EUI fuel system consists of 5 major components. Electronic unit injectors produce fuel injection pressures up to 30,000 psi and fire up to 19 times per second at rated speed. The fuel transfer pump supplies the injectors by drawing fuel from the tank and pressurizing it between 60 and 125 psi. The ECM is a powerful computer which controls all major engine functions. Sensors are electronic devices which monitor engine performance parameters such as pressure, temperature, or speed, and supply this information to the ECM by means of a signal voltage. Actuators are electronic devices which use electrical currents from the ECM to change engine performance. An example of an actuator is the injector solenoid. Now that we've introduced the major system components, let's discuss the operation of each component in more detail. We'll start with the mechanical components and then cover the electronic components. Diesel fuel systems use a plunger and barrel to pump high-pressure fuel into the combustion chamber. The cam lobes, push rods, and rocker arms mechanically actuate the injectors. The term EUI is actually an abbreviation for mechanically actuated, electronically controlled unit injector. Major parts of the injector include the tappet, plunger, barrel and body, nozzle assembly, and cartridge valve. The nozzle assembly consists of a nozzle spring, nozzle check, and nozzle tip. The cartridge valve consists of a solenoid, armature, poppet valve, and poppet spring. The injector is mounted in an injector bore in the cylinder head, which has an integral fuel supply passage. On older engines, the injector seated on a brass sleeve, which was swaged into the bottom of the injector bore. The brass sleeve provided a combustion seal and separated the injector from engine coolant in the water jacket. On 3406E engines, an improved stainless steel sleeve is used. This sleeve also separates the injector from engine coolant, but the injector actually does not touch the sleeve. Supply fuel is sealed above the sleeve by an external injector O-ring, and the cavity between the injector and sleeve is empty. The injector nozzle case seats directly on the cylinder head to provide a more positive combustion gas seal. The sleeve is installed with a light press fit and O-rings rather than the mechanical swaging used on brass sleeves. Increased wall thickness on the stainless steel sleeve allows the use of internal threads. These threads make sleeve installation and removal much easier. C10, C12 engines also use a stainless steel sleeve similar to the 3406E. Rather than using O-rings, this sleeve fits in the cylinder head with a light press fit and is sealed using retaining compound on the upper and lower lands. Actuation refers to the type of force used to power the plunger, which pumps the fuel out of the injector. Mechanically actuated fuel systems use a camshaft lobe and rocker arm to provide that force. The rocker arm presses down on the tappet at the top of the injector. The tappet, in turn, presses down on the injector plunger, which pushes fuel from the plunger cavity below the plunger. Fuel displaced from the plunger cavity can flow in two directions. Fuel can flow to the nozzle assembly and to the nozzle tip. However, to flow out of the tip, the injection pressure must reach about 5,000 psi in order to raise the nozzle check against the force of the nozzle spring. The fuel chooses the path of least resistance. It flows around the normally open poppet in the cartridge valve assembly to the fuel supply passage in the cylinder head. When injection is desired, the ECM sends a current to the solenoid on the cartridge valve. The current creates a magnetic field, causing the poppet to close. Fuel flow past the poppet is blocked, and pressure begins to build from the poppet through the plunger cavity to the nozzle check. When the pressure reaches approximately 5,000 psi, the force of the high-pressure fuel overcomes the spring tension holding the nozzle check closed. The check lifts off its seat and fuel flows out of the orifice holes in the nozzle tip. This is the start of injection. The rapid flow of fuel out of the plunger cavity is restricted by the very small orifice holes. Because of this restriction, injection pressure continues to rise very rapidly, even after the nozzle check opens and injection begins. Injection pressures continue to rise until the flow rate out of the orifice holes equals that of the fuel leaving the plunger cavity. Depending on engine speed and fuel delivery, this pressure ranges from 10,000 to 30,000 psi. High injection pressures promote complete combustion and lower exhaust emissions. Pushing the fuel through the orifice holes in the nozzle tip causes the fuel to atomize into droplets in the combustion chamber. Fuel droplets burn from the outside into the center. Large droplets take longer to burn and may not have time to burn completely during a normal combustion cycle. Increasing the pressure of the fuel through the orifice holes creates smaller droplets. In turn, smaller droplets burn more completely. There are 4 stages in the operation of the EUI: pre-injection, injection, spill, and fill. The first stage, pre-injection, starts with the plunger and tappet at the top of their stroke. The plunger cavity is full of fuel, the poppet in the cartridge is open, and the nozzle check is closed. Fuel leaves the plunger cavity when the rocker arm pushes down on the tappet and plunger. Fuel blocked by the closed nozzle check flows past the open poppet to the fuel supply passage in the cylinder head. As long as the solenoid on the cartridge valve is not energized, the poppet remains open, and fuel from the plunger cavity continues flowing into the fuel supply passage. To start injection, the ECM sends a current to the solenoid on the cartridge valve. The solenoid creates a magnetic field which attracts the armature. When the solenoid is energized, the armature lifts the poppet until it contacts the poppet seat. Once the poppet closes, the flow path for the fuel leaving the plunger cavity is blocked. As fuel continues out of the plunger cavity, pressure builds very rapidly. The poppet transfers this pressure through the plunger cavity to the nozzle assembly. When fuel pressure reaches approximately 5,000 psi, the nozzle check lifts off its seat and fuel flows out the tip. This is the start of injection. Injection pressure continues to build very rapidly until the same volume of fuel, pumping out of the plunger cavity, sprays from the tip. Injection occurs as long as the plunger continues to move down and the energized solenoid holds the poppet closed. When it decides that injection should end, the ECM stops current flow to the solenoid. This collapses the magnetic field holding the poppet closed. Spring and flow forces open the poppet almost instantly. High-pressure fuel can now flow around the open poppet and into the fuel supply passage. With fuel injection pressures approaching 30,000 psi, The velocity of the fuel flowing around the poppet into the 100 psi fuel supply passage is very high. This results in a rapid drop in injection pressure. When injection pressure falls to about 3,500 psi, the nozzle check closes and injection stops. This is end of injection. The extremely fast pressure drop from peak injection to end of injection reduces particulate emissions and is an important benefit of EUI. Let's review the operation of the cartridge valve, which is the heart of the EUI injector. In order to perform correctly, this valve must be able to open and close almost instantly, seal injection pressures of 30,000 psi, and prevent leakage of high-pressure fuel during injection. Containing these elevated injection pressures without leakage requires extraordinary manufacturing precision and tolerances. Any high-pressure fuel leaking past the poppet during injection is not delivered into the combustion chamber. The poppet valve opens and closes more than 500 million times during its normal wear life. The ability of the valve to function properly after hundreds of millions of cycles requires more than quality design and manufacturing. This level of durability requires proper fuel filtration to remove microscopic abrasive particles contained in the fuel. Abrasive particles smaller than 10 microns in diameter can cause accelerated wear in any high-pressure fuel system. That is why much finer filtration is being used on modern engines with high-pressure fuel systems. The difference between normal wear and excessive wear on a poppet valve seat illustrates the importance of proper filtration. On the left, you see a poppet valve seat with normal wear after extended use. Notice the condition of the sealing band on the poppet seat. While some wear is present from continued exposure to high-pressure fuel, the sealing band is still in good condition and providing a positive seal. The condition of the sealing band on the worn poppet is the result of abrasive damage from inadequate filtration. The damage to the sealing band is due to abrasive particles in the fuel flowing at high velocity past the poppet seat. This worn poppet seat leaks significantly during injection, resulting in low fuel delivery into the cylinder. In short, a prematurely worn injector. This condition can be avoided using proper filtration. Caterpillar offers high-efficiency fuel filters that meet the demands of newer high-pressure fuel systems and specifies the use of high-efficiency filters in many applications. Field experience demonstrates that these new filters more than double wear life of both new and old fuel systems over the former standard cat fuel filter. There's a good deal of confusion regarding filter ratings. One of the more common terms, micron rating, can be misleading. There may be significant differences in the ability of different brand filters with the same micron rating to remove very small abrasives from the fuel. Filter efficiency is commonly expressed in terms of nominal or absolute ratings. For example, a 5-micron nominal filter may only stop 50% of the 5-micron or larger particles striking it. In other words, every other 5-micron particle may pass through a filter with a nominal rating. Caterpillar high-efficiency filters remove more than 98% of particles 2 microns or larger. However, the rating of the filter paper means nothing if the construction integrity of the filter is faulty. In some cases, competitive brand filters constructed with leak paths allow large amounts of all size particles to pass. Caterpillar constructs its high-efficiency filters on a completely automated process, constantly testing to assure complete assembly integrity. Why is this fine filtration important? A recent study by a noted independent research agency confirmed that abrasive particles 5 to 7 microns in size cause most abrasive wear in fuel systems. These very fine measurements can be difficult to comprehend. This diagram illustrates the relative size between a single micron and a human hair, which is about 80 microns, or 35 ten-thousandths of an inch. The smallest particle visible to the naked eye, such as a speck of dust, is 40 microns. Particles as small as only a few microns can cause significant wear due to the extremely high pressures. This example shows the difference in efficiency between a Caterpillar high-efficiency filter and a typical 5-micron nominal filter. The CAT filter removes more than 98% of the 5 to 7 micron abrasive particles in the fuel. The 5-micron nominal filter only removes about half of these particles. This is assuming that the filter contains no leak paths, allowing abrasives to flow around the filter paper. Over time, these additional abrasives cause accelerated wear in any fuel system. This includes pump and line systems that operate at significantly lower pressures than EUI. Accelerated wear is more pronounced when the fuel contains unusually large amounts of contaminants. A good example of this problem occurred several years ago in a logging application. The customer operated log skidders with pump and lines fuel systems and complained that the fuel injection pumps were wearing out in as little as 2,000 hours. Subsequent investigation revealed no manufacturing defects, so abrasives in the fuel were suspected. The customer was using the standard Caterpillar 15-micron filter, so many of the abrasives were smaller than 15 microns. Testing the theory, which states very small abrasives are at fault, a side-by-side test was run with completely rebuilt pumps on the two identical machines. One machine remained equipped with the standard 15-micron filter, while the other machine was equipped with a high-efficiency 2-micron filter. Instead of changing filters at the recommended 250-hour change interval, both machines ran to 1,000 hours to see if the finer filter would plug from extended use. It didn't. After 2,000 hours of use, both pumps were disassembled and inspected. The pump using the 15-micron filter suffered significant abrasive wear, while the one using the high-efficiency filter looked and performed like new. These findings led to the testing of the high-efficiency filter in other severe applications around the world. In some countries, fuel lubricity is poor, and the fuel is loaded with very small abrasive particles. In these severe applications, the average life of many unit injectors in excavators has been about 1,500 hours. In extreme cases, injectors have worn out in as little as 200 hours. Since the introduction of high-efficiency filters in these applications, there has not been a single case of a documented system wear-out. Follow-up investigation shows some former problem machines now have over 5,000 hours of operation with no sign of injector wear. There are many other examples of dramatic improvements in fuel system life using high-efficiency filters. The improvement